Hello everybody and welcome back to the 2000 Fermat paper. We're on to question number 16. So, the digits 2, 2, 3, and 5 are randomly arranged to form a 4-digit number. What is the probability that the sum of the first and last digits is even? So immediately what strikes me about this question is that they're asking us for a probability. And so we can double check that. There's a whole bunch of fractions in here. And so if we're asked for a probability, we need to figure out two things. First thing we need to figure out is how many of the outcome that we want actually happens. So how many 4-digit numbers do we have where the sum of the first and last digits are even? And then we need to figure out the second thing. We need to figure out the total possible number of outcomes. So that is the number of possible 4-digit numbers you can make this way. Then you take the first one divided by the second one, and then you have your probability. Number of desired outcomes divided by total number of outcomes. So we have two things we're going to be doing. So we can choose either one. What I'm going to do first is I'm going to figure out how many possible 4-digit numbers we can make with these digits. And then we'll worry about the even last digits adding up to, the first and last digits adding up to an even number. Okay. So we grab our pen, we grab a scrap piece of paper here. So we have 2, 3, and 5, and we want to rearrange them. Now, if these were all different numbers, we would rearrange them and we would have 4 factorial, that's 4 times 3 times 2 times 1, different ways of rearranging them, the permutations. But the problem is we have 2 of them that are the same. Okay? Now there's a formula for how many ways you can rearrange things if you have multiple copies of something. And so if now I don't think I want to write out the general formula. I have in other contest videos, so I encourage you to track those down or just look it up online. Rearrangements with copies or duplicates would be something that you could easily do. But basically what you do is you take however many things that you have. You start with that 4 factorial, and that's correct. And then for each set of duplicates, so maybe you've got 2 2s or maybe you got 3 5s or something like that, you just divide by the number of each different type of object. So we have 2 2s, so we're going to divide by 2 factorial. We have 1 3, so we divide by 1 factorial, and we divide by 1, and we got 1 5, so we divide by 1 factorial. Now, as an aside, suppose we were trying to make numbers out of 3 3, 7 7, 7, 5, 2 2. Maybe we were trying to do that. Just because I don't want to write down the rule, but I would like to illustrate it a little more for you. So we have 1 2 3 4 5 6 7 8 things to rearrange. And we want different, distinct numbers we can make with these digits. So we have multiple 3s. How many 3s do we have? We have 2, so we divide by 2 factorial. We have multiple 7s. How many 7s? We got 3 7s, so we divide by 3 factorial. We have 1 5, so we divide by 1 factorial, and we have at last 2 2s, so we divide by 2 factorial, because there are 2 2s, not because it's the number 2. And you'll know you're doing this right because the number on top will be the sum of the individual numbers at the bottom. Okay? These are sometimes called multinomial coefficients. So if you're familiar with Pascal's triangle binomial numbers, this is right up your alley, and it's something else that you can search for. Multinomial, M-U-L-T-I-N-O-M-I-A-L, multinomial. But it's the number of rearrangements when you have copies or duplicates. But I don't want to dwell on this for too long, but we can use this. And it turns out that as long as you follow those rules, as long as these guys add up to the number on top, then it's always going to work out. You're always going to get an integer number. So in this case, we have 24. 24 on top divided by, well, it's 2 factorial, that's 2 times 1 times 1, so this is just going to be 12. So there are 12 different 12 different numbers. Okay, so now we know sort of the sample size. We know how many possible 4-digit numbers we have. Now for the other thing we need to know for probability, how many have the desired outcome? How many of these 4-digit numbers have the first and last digit add up to an even number? Okay, so that's the next thing we need to figure out. And it could be all 12. It won't be, but it could be. In which case then it would be 12 divided by 12. And we'd get a probability of 1. Or maybe none of them work out. We get 0 out of 12. But it's probably going to lie somewhere in between. Now, there's 2 ways to go about this. 12 is such a small number, we could probably write out all 12 different 4-digit numbers. Okay, and that's perfectly reasonable way to do it. But I'm going to do it in a different way, where we explain our reasoning, we explain our choices, we break things down into cases. And the reason is, I want you to understand the logic, because maybe the next time you see this question, it'll be on a Euclid or maybe a national math paper, math Olympiad paper or something crazy, where you don't have 12 that you could just easily write out. Maybe it'll be 50 things, and you don't want to write out 50 6-digit numbers. So we're going to show some reasoning, we're going to show some counting arguments, and this is sort of the essence of introductory combinatorics. So the condition we need to satisfy is first and last digits are add up to an even number. So let's write out A, B, C, D as our digits. Okay, so A could be 2, and B could be 2, and C could be 5, and D could be 3, who knows? But we know we want A plus D to be even. So that'll equal an even number. Okay. But A and D come from this set. So what are the possible choices for our pair AD? So 2. Well, I could have 2 be the first and 2 be the last, and then I'd get 4 as my sum, and that's even. So AD could be 2 and 2. Could I have 2 and 3? Well, no. If the first digit's 3 and the last digit's 2, that adds up to 5. That's not even. How about 2 and 5? No. 2 and, I mean, we could do all the same argument with this 2, but it's going to be identical to the first 2. And the only other pair we could really have is 3 and 5. Okay. So we have 2 different cases. First, let's explore what happens when A and D are the 2s. And then we'll explore what happens when one of A is 3 and the other one and D is 5. So we have 2, B, C, 2. So how many numbers can we make out of 2, 2, 3, 5 that start with 2 and end with 2? Well, our 2's are spoken for, so B is either 3 or 5. We have 2 choices for B. B equals 3 or B equals 5. And once we pick B, C is forced to be the other number. So C doesn't really have a say. As soon as we have picked something for B, we know what C is. So since there's 2 choices for B, there's just going to be 2 numbers. We get 2, 3, 5, 2, and 2, 5, 3, 2. So those are our 2 possible numbers that start with 2 and end with 2. So that's one case. Now suppose A is 3 and D is 5. And since we're splitting it up, I guess we can write this case over here. So 3, B, C, D. But wait a minute. The 3 and the 5 are spoken for, so B and C are both 2, so we only get one other number. 3, 2, 2, 5. And if A is equal to 5 and D is equal to 3, we don't have any choice. We have to have both the 2's to be in the middle number. So 5, 2, 2, 3. That's the only possibility. So once we have picked our two odd numbers to be on the outside, the two 2's have to be in the middle. And there's no distinction between 3, 2, 2, 5 and 3, 2, 2, 5. Did you hear that? Did you see where I rearranged the 2's? No, you didn't, because it's the exact same thing. It's the same number, it's the same 2. So we don't get multiple choices. B and C have to be 2. So there's only one number, 3, 2, 2, 5. Likewise, we only get 5, 2, 2, 3. So there's two numbers here, one number here, one number here. So we've got 4 different numbers. So 4 numbers satisfy the condition. And that means that our probability is the number that we want, which is 4 numbers satisfy the condition, divided by how many possible numbers there were. That's 12. And that easily reduces down to 1/3. And I believe 1/3 was one of the answers. Yeah, it's B. So we get B is our final answer. Okay. So that does it for that question. We're on to question number 17 in the next video, and we're almost done part B. But we'll have to wait for those really, really hard, nice and difficult and expertly challenging questions in part C. But we're going to have to wait, and we'll have to go through 4 more questions before we get there. So I'll see you for question number 17 in the next video.